Thank you for bearing with us while we got the camera rolling so that people can tune in after the fact. Good morning, I'm Jacqueline Feldscher, the managing editor of Payload. Thank you so much to Redwire for hosting this panel on how autonomy is changing the game in space. I do want to point out at the very start, we're going to be taking audience questions, so if you have questions as the panel goes on, please make sure to note them, and we will get to them a little bit later. I'm thrilled to be joined today by our panel of experts representing all different sectors of the space community, so I think we can have a very diverse discussion. Today we have Benjamin Bahney, the program leader for space at Lawrence Livermore National Laboratory, Dean Bellamy, a retired Air Force colonel and current EVP for National Security Space at Redwire, Dr. Seth Lacy, the senior scientist for space mobility and precision maneuver at the Air Force Research Lab, and Colonel Owen Stevens, the director of contracting at the Space Force's Space Rapid Capabilities Office. So to start off with, I'd like to invite each of our panelists to briefly introduce themselves and share how their office fits into this push for more autonomy in space missions. And Seth, we'll start with you.
Very good. So I'm from the Air Force Research Laboratory, and our job is to build technology for the Space Force and the Air Force. So we have two customers for our tech, and some of our primary customers are the acquisition organizations within Space Force. So Space RCO, Space Development Agency, and Space Systems Command are the three acquisition orgs in space for the Space Force. So we build tech for all of those, and we also perform our own internal flight experiments to go and test and validate technology. And our engineers are the same folk that put the payloads together and build the spacecraft, are the same poor guys that have to go and operate the spacecraft. And so we come at autonomy from that perspective of we don't like getting up at 2 o'clock in the morning when something goes wrong. And so we like to automate things to make the operations smoother for our humans.
We can just go straight down the line, Dean, if you want to go next.
Oh, awesome. Thank you, Jacqueline. I appreciate that. For folks who are not familiar with Redwire, we're a multi-domain company. We're building autonomy in our uncrewed air vehicles, or UASs. There's a lot of autonomy there. We're also doing a lot of autonomy in our VLEO satellites, both in Europe with our Phantom satellite and our SabreSat here, VLEO satellite in the US. And we can talk about that. We'll talk about that today. We're also, when you start looking at our GEO spacecraft, we're on a program called Tetra 5, Tetra 6. We're building a lot of autonomy in for that. And then we're doing a lot of partnerships with academia like Stanford University and their autonomous lab called Caesar, where we're really building state-of-the-art cutting-edge autonomy. And lastly, on the software side, for AI tools and autonomy, we have a capability called Acorn 2.0, where we have agent-based modeling for modeling and sim to do really cutting-edge mission concepts, and we'll talk about that today.
Yeah, hi, I'm Ben Bahney from Lawrence Livermore National Laboratory. For those of you that aren't familiar with Livermore Lab, we are a Department of Energy federally funded research and development center at FFRDC. What are we doing in space? Well, Livermore Lab is specifically really trying to help the U.S. government really broadly on the broad set of space warfighting missions, including space domain awareness and space mobility. In particular, the DOE National Labs are home to some of the nation's most advanced physical test and simulation infrastructure. The Department of Energy, in particular, is one of the biggest investors in R&D in the entire U.S. government, particularly in hard infrastructure. So really what we're trying to do in the space program at Livermore is to try to leverage the capabilities of the Department of Energy National Labs, but for space security mission sets. So in particular, because of all of our capabilities in computing, we have the world's most capable high-performance computer called El Capitan. It's about 2.8 exaflops, so that's about 1 million high-performance desktop machines strung together, an equivalent amount of computing capability. There are certain problems in the autonomy space that you can only really solve through machine learning applications through high-performance computing capability. And we're trying to leverage that in support of the DoD mission area.
Hi, I'm Owen Stevens, Director of Contracting, Space Rapid Capabilities Office. Our office is primarily concerned with orbital warfighting. Most of what we do we can't really talk about publicly, but just think orbital warfighting. We do some number of enabling capabilities that some of you may or may not have run across in the public sphere. So for example, we're building a common ground system for use with all of our satellites and all other satellites concerned with the same activities. R2C2, the software program is called ACME, and we will be building kind of autonomous hooks into that system. And then we have another one kind of revolving around the same autonomy discussion, satellite communication augmentation resource. And it's a phased array that will do some number of simultaneous contacts. And so for that one in particular, autonomy, you start wondering, how do I manage this activity? Because a human being will quickly run out of the ability to manage that activity. So autonomous scheduling, finding the right antenna resources, and all of that. So and then in terms of satellites, there's two kind of autonomous activities we're interested in. One is concerned with like just the daily care and feeding of satellites. You'd really like to go to lights out for that and only concern people with things people need to be concerned with. You really need a person to manage a TT&C, right? That isn't a thing that you want to waste your resources on. And so that part, and then also when you start thinking about space as a warfighting domain, you quite likely will want your satellites to autonomously react to certain things. And so autonomy in that nature as well. And I guess that's it for an introduction. Thank you.
Great, that's all super helpful context to kick off our discussion today. I want to start by diving deeper into sort of why we're having this conversation now. We all know that space is getting more congested and more contested. So Benjamin, I'm hoping you can start off on kind of why industry and the military need to be talking about autonomy now.
Yeah, I think there's a couple things happening that make this discussion particularly salient right now. One of them is the massive growth in the use of space, primarily driven by the reduction of cost of launch, right? So we're seeing thousands of satellites now go up every year, massive constellations, which get to this problem of the care and feeding. Secondly, we're seeing more rendezvous and proximity operations in space, right? So we're seeing more individual spacecraft trying to get in close to other spacecraft. And in a situation like that, autonomy could be very valuable. Third, another thing that we're seeing is U.S. competitors really starting to invest in spacecraft autonomy for a variety of applications. And I think with that in mind, we start to think about, well, okay, if the other side has autonomous capabilities, is it possible for us to compete with that with a human in the loop around the loop? And then last, there's also the dramatic expansion of activity into lunar orbit, right? And once you get outside of geo communications are hard enough. You get really link budget limited, right? Doing communications out in those regimes is very challenging. And so there's tremendous benefit if you can operate autonomously, reduce the amount of link budget if you're doing sensing. Also, if you can do sensing at the edge, right? If you can do edge processing and downlink, there's a huge advantage to that. And I think we're starting to see technology get mature to the point where you can start thinking about applications in that space, but I feel like there's still significant hurdles.
Dr. Lacy, Dean, do you wanna weigh in on that?
Yeah, absolutely. Thank you, Jacqueline. I would agree with everything Ben said, and actually Colonel Stevens said. I remember as a second lieutenant sitting at Onizuka, and I was in Space Ops Center 38, and we had a checklist for doing those mundane, like, temperature readings and all that, and I'd have to go through with a grease pencil. Yes, we used grease pencils back then, and actually check off the steps and then send the commands up. But what we're seeing today is those tasks shouldn't be done by humans on the ground. And one of the things we're doing at Redwire with our Tetra 5 vehicle, we're looking at for the vehicle to be able to sample, and if it has a temperature reading, or if it needs to turn on a heater, that the satellite will be able to do the carrying feedings for itself, and then send, kind of like ET, send a beeper back home, send a command back home saying, hey, this is the actions I've taken. To perform, so the Guardian operators on the ground will actually get information and understand what's been going on. And I think that's really key because as Ben said also, when you start looking at these mega constellations, there's not enough RF antennas on the ground, there's not enough comm bandwidth to do bus capabilities. It really needs to focus on the mission and getting the mission data, actionable information from the payload to the people who need it.
Dr. Lacy, want to come to you. Kind of a similar question. We all know DoD has been hit. Really, the whole federal government has been hit with a lot of personnel cuts. So how is your office thinking about like how autonomy will help as the people asset is cut?
So within the confines of the Air Force Research Laboratory, we don't fly any mega constellations. Of course, within the space work, we are looking at large constellations for things, and so we're trying to build technology to go and enable those constellations. You're not going to operate those with 10 humans per spacecraft or anything close to that. So they need to live on their own, and even more than that, it's not just in a normal time. They need to be operable even in conflict with a small number of humans. If you have to staff up to 10 humans per spacecraft, that's not tenable either. So that's kind of the bigger version. Locally, within our own little research world, we just don't have that many humans to sit around and operate spacecraft in that 10 humans 24/7 kind of construct. We just don't have that kind of staffing, and our engineers don't like doing it, so they tend to engineer themselves out of that job. So they'll look for ways, how can I automate this? And we're looking at all different, so very script-based, if-then kind of things, as well as more, okay, what could we do if we, applied some machine learning or AI or something to this problem? Can we be more predictive about this? And we've had some pushes in that direction. So, what can we do to enable our spacecraft to be more functional with fewer humans? And we're finding you can get, you're not trading functionality. You may in fact be increasing functionality because you're doing things with automation that you wouldn't want the humans to do anyway. Humans are terrible at remembering 10 numbers in a row and typing them in correctly. Humans are terrible at hitting the right number of things in the right order. Like, that's not what we're good for. Machines are, and so we've seen a lot of examples of increased reliability and decreased human load.
Colonel Stevens, over to you from the contracting perspective. What are you looking for when it comes to autonomy, and are you seeing enough of what you need as you go out to partner with commercial companies?
No, but that's mostly our fault. So you might see a thing in the contract says, give me autonomy. And then we leave it on the company or whoever we're contracting with to figure out what that means and then say it back at us as an engineering derived requirement or whatever. And I think as a general statement, the government doesn't take enough time or give enough thought to what they actually want. I found we don't do that very well. And I'm not one of those people that thinks that AI or whatever can provide that for us, because you have to give it good data to begin with to learn the problem in order to describe the language you want. A human needs to think about it first, so that the machine can learn. So I'll pick up a few of those points. The government needs to figure out what things a machine can do better than a human, and there's a lot of those things, and he described a few. And then we need to say, these things that a machine can do better than a human, I want you to automate that. I want you to script it out so that we're doing, so that the machine is doing that work. And then what other things don't I want a human being doing so that I can shift his resource over to the things we do want them doing that a human must do. And there are a few things that a human must do. And describing those, instead of treating it like a buzzword, give me autonomy, right? And then develop along those lines, and then you need to step back a level and think about it from at a kind of a systems of systems. So if you have a ground control system that has autonomy built in, but in its path to get to the satellite, it can't do that in a machine-to-machine manner, well, then you really haven't accomplished anything, right? So you need to step back and look at the whole system end to end and go, okay, I want a machine to do this for me, but I want it to be all machine from one end of the sequence to the other end of the sequence. What does that now look like? And then you start talking about other weaknesses or enablers that you need to have in place. So for example, do I have the available, long haul for my bits as they travel across the country? Is that robust enough? Do I have resiliency? Do I have multiple comm pathways that I can choose so that I can do machine to machine all the way across, and somebody on the floor doesn't have to pick up a phone and call somebody else on the floor and go, hey, would you please do this for me? Because we do that, right? And so the government needs to step up a level after figuring out what a machine wants to do, step up a level and consider what that means from one end of the ecosystem to the other end of the ecosystem.
Dean, I want to bring you here, kind of how from a commercial's perspective, you are taking that order and kind of how you are adapting to meet the military's needs.
Yeah, that's great, and I echo what Colonel Stevens just said. One area that we're doing it is, and I mentioned this a little earlier, we have a capability called Acorn 2.0, where we're doing agent-based modeling, and it's really building out the mission concepts. And we're doing this early when we're even in the proposal phase of looking at a program to transition of starting a program, we're using this digital engineering ecosystem, and we're really understanding, just like Colonel Stevens is saying, what areas should we have autonomy? What areas should we be actually doing things better? One area might be, for example, with optics, right? If you're going to be doing a space domain awareness mission, how much maybe sensing or onboard computing do you need versus how much stuff do you send to the ground for processing? And we iterate those trades and we look at that, and we work with a lot of great partners in industry and academia, also with folks like Livermore here in DOE and others. And I think that what you see is that whether you're working with Stanford University or others, we are actually getting cutting edge and really state-of-the-art capabilities, and we're using that to actually offer, I think, affordable as well as the best-in-class kind of capabilities for what autonomy should be. And Seth, you're 100% right when you said earlier, a lot of it is going to be some of these if-then statements or machine learning statements, or it could be even more than that. And so I think that by bringing in people from across industry, across the community, to really look at where we should apply it and how we apply it in an affordable way.
So please go ahead.
Yeah, thinking about the autonomy looks different depending on the mission. So an autonomy stack that you might fly in low Earth orbit is going to look different than something that you're going to fly in cislunar, where you have degraded comms are the best comms you're going to get. It's unpleasant from that perspective. Going down into very low Earth orbit, where propulsion now is kind of a critical thing. If you're a spacecraft, we design a lot of spacecraft that are designed for recovery, not for 100% will never reboot. So that's a philosophy, and mostly from a cost perspective, research budgets aren't that big, so we have to buy pretty low reliable hardware and work with it. But if your spacecraft reboots and goes into a tumble and then you recover it a day later, that's not a big deal in low Earth orbit or other regimes. Whereas in very low Earth orbit, oh no, I need to get it recovered. Propulsion has to get turned back on again because if I don't, the thing is going to re-enter. So there are different levels of autonomy, different flavors of autonomy for these different orbital regimes.
So I think, we've touched on, kind of mentioned a couple missions. You talked about RPO, talked about space domain awareness, but hoping to dig a little deeper into, missions in space that are well suited for autonomy, or, specific parts of missions that you do see that, autonomous nature that is good to introduce autonomy. Seth, we can start with you on this.
I think we like to think of the automation as something we're going to do from the very beginning. And that can start even at the hardware level, where you may design, okay, I will have some high reliability watchdog timer or something that has to get pet. It will keep track of low reliability hardware and reboot things or something, or power cycle them if they need to be power cycled. So even starting at that very early design architecture phase, how is my hardware going to look? We want to think about, all right, how am I automating this? And how am I thinking how this is going to enable the mission, once I actually get the thing on orbit. We do tend to learn a lot during operations, and so the other end of that journey, we discover anomalies that maybe we hadn't thought about, and we will automate responses to those. That's very reactive. We automate the responses to the things we have experienced, and so that's you develop scars and you learn from those. And we're trying to think of how we get past that and become a little more predictive about, okay, how do we automate this for scenarios that anomalies that we have not. Creativity is only so much. We only get you so far. And once we get these really complex systems, many spacecraft working together, networking, layers on top of that. The complexity and emergent behavior can sometimes give you results that you did not predict. How do I prepare myself to automate my way out of those experiences?
Colonel Stephen, same question to you. Kind of how you're thinking about areas or missions that are well suited to autonomy from your position, or if there are areas where you say this is best for a human and really can't be automated. Kind of the flip side of that coin.
Okay, so in my term talk knows that I generally eventually draw the conversation around the airplanes, because airplanes are cool. And I'll do that at this point in this conversation. The air-breathing world has decades upon decades of experience dealing with these issues, and I won't say that they've dealt with them optimally, but they've learned a lot over time. And so, for example, you get a modern fighter, and he experiences a set of conditions, and the airplane goes, oh, that set of conditions means that I must punch chaff and flare now without even bothering the pilot, right? And so the reason that they've gotten to the point of that learning, back to your point, is they have a robust ability to do, they call them flag exercises and other things, where they actually flag against each other in mock engagements, mock scenarios, and they learn. And through learning, they develop tactics, techniques, and procedures that apply. And then in some cases, they go, oh, that would be a wonderful TTP to automate, so that a human doesn't have to do it, perhaps because a human doesn't have the reaction time to do it appropriately. We have a dynamic going on with the Space Force in space right now, in that we're scared to use our satellites. We're scared because they'll have only so much Delta V available for their lifetime, and we have so few objects that it's like, oh, I really don't want to maneuver this satellite. I don't want to practice. I don't want to play around with this so that I can learn from it, because once I use that up, my next one is 3 years in the future, 4 years in the future. And so we really need to enable the ability for the Space Force to get relieved of that psychological burden and actually start using their machinery so that they can learn from and they can develop TTPs, and they can figure out, oh, this would be a really good thing to automate. And for space, it's even more important because the delay time, the lag between getting a human to decide what a satellite is going to do is like really extensive. And you really probably do not want that. And so what does that mean? That means we need to figure out how to start affordably producing more satellites, and or figure out how to introduce the ability to refuel satellites so that they have more delta V. And so those will enable us to figure out how to choose the things we want to automate that are smart to automate, because you do have to learn. To his point, you have to learn. There are some things you go, okay, we'll just automate that. Like, there's no reason to do like a normal care and feeding contact in a non-automated fashion. You shouldn't need a human to do that, right? In fact, the machine will do it better than a human could, because they'll screw up in their little command entry. How many did you screw up?
Probably a handful, right?
Yeah. So let a machine do that. Let a machine figure out the optimal antenna to do the contact. Let a machine figure out all of those things, and then the humans can start figuring out the rest of the picture. What does it make sense to automate, and why does it make sense to automate it?
I think the fact that refueling or launching a larger satellite with more fuel, the kind of that technology gap that would allow more experimentation, more like wargaming and testing. That's fascinating. Benjamin, I want to come to you on kind of other technology gaps that need to be closed to make autonomy more useful for dynamic space.
Yeah, I think one of the things we're working on for dynamic space is we have a collaboration with MITRE to try to simulate different courses of action for different types of kind of rendezvous and proximity operations for space domain awareness. And this is an area where I think operators could use more training aids to understand what's possible. And so here we're trying to use machine learning to come up with optimal maneuvering strategies with regard to a non-cooperative vehicle. And actually this is where you really need massive computing solutions to make this work. This is why MITRE and we are partnering together, because we can bring massive scale computing to this area. But I think that's where there needs to be a technology push from people that know how to run algorithms on massive compute, how to get answers back that can actually help operators understand what's physically possible. So there's the courses of action kind of technology development to help people understand what you can do. There's also, I think, in space, for space sensing, I think there's a real challenge with, as I mentioned before, the link budget problem. Something we're driving a multi-year research campaign forward on is trying to develop space domain awareness optical solutions, so wide field optical systems to survey the entire massive volume of deep space like cislunar space, and then to do compute at the edge, because fundamentally you're going to be link budget limited, you're going to be limited by what you can do on the ground. And so really what we're trying to do is design optical systems with onboard computing that can sense in that wide volume of space with enough coverage and revisit to actually get all the data that you need, but then also reduce it at the edge. And the challenge there is really onboard computing. And so we've been flying GPUs on all of our optical systems in space. We feel like that's got to be a part of the future solution set. We have other FFRDC partners that are flying other types of technologies in partnership with AFRL, again for space sensing. And so I think there's really kind of a hard technology problem at the edge that still is not solved. And I think there's a little ways to go yet on that. So that's just a couple areas. I think a third one is really understanding standards. And so this is an area I think where the government can kind of help work with FFRDCs to lay out what the criteria are for future success. Colonel Stevens mentioned this earlier. One place where we've been trying to help with that is with the Space Domain Awareness TAP Lab. There we've been developing kind of a benchmark set of metrics for vendors to come apply their tools, and then we can actually do the scoring. It's a great role for an FFRDC. It enables industry. It helps government figure out what's better and what's not as good. And I think, really there, being able to drive forward this question of, what are the right metrics, what are the right standards for industry to try to go out and meet is an important role. It's something that requires, I think, more work on the government side. But I think there's a lot we can do there in the near term.
So Dean, from the commercial perspective, how are you working to address some of these technology challenges on the industry side? And what challenges are you facing internally as you try to develop these programs when it comes to automation?
Yeah, great question. I'd really like to follow up on Ben's point. Having common standards is so important. So really encouraged and really proud of the work they're doing to really come up with a standard. Really the key there is to be able to connect, access, and share data, across multiple vendors or third parties. And that's so critical for us to have that common set of standards for us to operate. And I think autonomy, well then you could look at areas where you can do autonomy on top of that. So really, really excited about that and excited to see how that continues to assist all of industry and government on that. The more interoperability we get really is what that's enabling, and it's really phenomenal. The other area I'd follow up with, both with Seth and Colonel Stevens talking about, autonomy and learning. And I love the airplane analogy, so I'll use it too, right? So a lot of people probably love the movie Top Gun Maverick, right?
That's the Navy.
Absolutely, it's a great movie, right?
It's a great movie, but it's the Navy.
It is. It is the Navy, but I'll use it. Autopilot, right? Planes have autopilot, right? So when we look at the ability as space gets more congested as a warfighting environment, the ability to ensure the mission can operate through an environment that could be, jamming or other kinds of, areas where people are trying to deny the ability for the satellite to operate. Having that autonomy where it can fly through and continue to provide the data to the soldiers, the sailors, the airmen, the guardians, on the ground that need the data is really critical. So to get that data from space to the ground is critical, and I think autonomy is going to play a big role there. And if you look at Tom Cruise and his character Maverick would not have been successful without autopilot, right? Being able to help fly the plane and alert him when things are going on. And I think the second area, when you look at Top Gun Maverick, right, they have a lot of autonomy on board. Right, he gets indications in morning with sensors on board that tell him, alert him of the environment. And I think when you look at satellites, today cars do this all the time, right? Whether you have an electric car or not, you get a lot of alerts. And I think having better autonomy on board for safety of flight and safety of the vehicle. So, 4-ply straight in, 360-degree view around a spacecraft. Similar to a Ring camera at home, everybody probably has a Ring camera at home where you get alerts for people if they're in proximity and near your vehicle. I think that would be another area.
Please.
Okay, so that's a really good point, Dean. So think in terms of not autopilot, but a related system, auto ground collision avoidance system, auto GCAS. Why did they put auto GCAS on all airplanes? Because people can't recover them every time and then they crash, right? And so we discovered that autonomy was the right way to deal with a very real problem in aircraft. Well, there's a chance of collision up in space too, right? So is there a comparable thing called not auto ground collision, but auto debris collision avoidance system? The problem is when you start unpacking a thing like that, it ends up with just to say it, it's like, oh wow, that took 5 seconds. It's really easy to say, it must be really easy. No, you start unpacking it and you go, okay, what do our TLEs look like? Are they actually accurate enough to enable the autonomous nature of a system like that? The answer right now is probably no. He's shaking his head, he knows more than I do. It's probably no. And so I'll reference back to my system of systems thing. You actually have to consider all the enabling functionality you need in order to make these things a reality, and you have to spend money and resources on those too to get them where you need to have them if it's a thing you want. Many times we just go, I'm going to do that thing, and I'm not going to think about any of the underlying technologies or foundational things that must be better, and then we do it doesn't work that well, and then we go, well, why did that happen? Well, it's because we didn't give enough thought to it up front. And so I think another opportunity to like pause and actually think about the thing you're trying to do a little more deeply than maybe what the government does from time to time.
So we're going to turn to audience questions soon, so everyone get them ready. But before we do, I mean, it's pretty clear listening to all of you that you see a lot of pros to autonomy, that it can, provide a lot of benefits for the military. Are there any cons? Whether it's, a culture issue of people not being ready, or, a possibility for mistakes. Like, what are the cons to using more autonomy? Please.
Who in here had their rental car flash a red dash at them, like here this week? Did anybody have that happen? Like okay, right there. Wasn't that scary?
Well, I'd never used Blue Cruise before. Just completely hands-free.
Yeah.
Driving 75 miles per 70 miles per hour. And I'd never been in a fully automated.
Somebody get his name.
Yeah. Pound vehicle. It was a big, giant, huge thing, and I'm like, well, somebody's dying. It's probably not me, but I could die too.
Yeah.
And then at a certain point, it did just like boom, put your hands back on the steering wheel now. After telling me to take them off, so that was shocking.
So I've got a pickup truck. It's old now, and it didn't do nearly what vehicles will do now. But the first time somebody got too close to the right-hand side of my vehicle, the seat started vibrating on the left-hand side of the seat. I'm like, what the? And so there's a human psychology factor at play there. Of course, I grabbed the steering wheel and tried to overpower the vehicle or whatever because I was alarmed. My wife, we just got a new Suburban High Country, and the whole like digital display will like start flashing red at you if you get too close to a car in front of you, and really freaked her out the first time. Actually, it still freaks her out every time it happens. But and then it steps on the brakes for you, and you want to control, right? So there's a human aspect of wanting to control that you need to let go of a little bit. The other thing is autonomy will make mistakes. That is a thing that will happen. Sometimes those mistakes will be really, really unfortunate and make a whole bunch of people really sad, mad, whatever. That is going to happen. Whenever you start building autonomy into things, because you haven't learned everything about it, sometimes the variables are so complex that it's kind of impossible for a human to envision every single variable. Then we go to generative AI that generates the algorithms for you or whatever, but it will make mistakes. That is not a reason to start running scared away from autonomy. That is an opportunity to learn from your mistakes, but mistakes will happen. Because that's what happens when you introduce autonomy to a scheme, right? Just kind of those two general areas.
Please, yeah.
I think another area, building on Colonel Stevens' comment, where I think there's some legitimate concerns about autonomy, is where you don't have good training data, right? Machine learning applications are great when you have a ton of training data, like, the classic one is finding cats in internet videos, right? Because there's a lot of cats in internet videos, it turns out. For space operations, and particularly for contested space operations, we don't really have a lot of good training data. Your point earlier about operators being afraid to use up scarce space mobility resources is a great talking point on that front. And so I think fundamentally, to really increase our ability to utilize automation for some of these areas, some of these mission areas, we need to think about that training data problem. And I think one of the solutions is synthetic data, and this is another area we've been helping the SDA TAP Lab with, where you can understand what potentially some of the constraints are in the environment. You can understand vehicle constraints, you can understand orbital mechanics constraints, you can build those into your simulation framework. You can build out emulations, right? You can create data that isn't necessarily real, but it's got a physics-based representation of the problem set. And so I think there are things, again, that FFRDCs can help to build in that can create some of the training data that can enable great commercial applications for some of these mission areas. But fundamentally, that training data problem, I think, is a really severe one. For space domain awareness, we have a lot of data. But again, we don't have a lot of data about what if things really go bad, right? We know how people act in peacetime. We don't know how adversaries are going to act in a conflict. And so again, having an intelligence-informed understanding of the problem set, having a very detailed, the most detailed possible understanding of the constraints. Those types of frameworks are what we're trying to work on at Livermore with our FFRDC partners. And I think there's more work to do there, particularly in that training data area.
I saw you pick up the mic, Dr. Lacy. Is there anything you want to add to that?
Thinking about the interface between the human and machine is very important. And so your example on the car, if the autonomy does something surprising to you that you don't understand, like I don't know why it just did what it did, that can be bad, and the human will turn off the autonomy. So we have that happen fairly frequently too, where we think we have a great idea, well ahead of launching a spacecraft, and this is going to be wonderful, and then it turns out it's a blinky light that comes on all the time, and everyone hates it, and so they turn it off. So that's one. Another one is that if it's not explainable, humans don't like it. If it's annoying, they don't like it either. Even if they understand what it is, like, oh, it's telling me I'm about to crash, which is, you would think, very important information, but a lot of times the humans will turn that blinky light off and be like, no, don't hit the brakes for me. I'll hit my own brakes. And so there's sort of two versions of that. One is sort of cultural, and maybe the humans can get used to it. Like, okay, fine, I'm not going to turn off the auto braking or something. But the surprising one is bad. So if you surprise the humans don't understand what's happening. Now the operator is, they're confused. Now they're fighting the autonomy. It's like, oh my God, I don't know what you're doing, and not focusing on mission.
Yeah, I would just add, one of the things that Redwire, being thought leaders on the engineering side, looking at this autonomy and AI, is really, foundational, putting the mission architects, the engineers together in a digital environment where we're like iterating on it digitally in our Acorn environment, to actually understand that, and actually having users like the operators who will either be on the loop or in the loop involved in that actually really plays a key role, I think. But you're 100% right. If it surprises you, right, that's never good, and people will turn it off, right?
Okay, great. Over to the audience. And please just identify yourself so we know who we're chatting with.
Yeah, I'm Andy Quass, a senior fellow at Northrop Grumman and Space Logistics. And with the undocking of the mission we did for 5 years and redocking to another satellite, plus our second mission extension vehicle, we now have 10 years combined of mission autonomy operations under our belt. And soon to have with the Air Force that we're working on the Air Force accepted passive refueling module. That's scheduled to be flown here very soon. And the mission robotics vehicle is scheduled for a March 26 launch. It's a long way to a question, Colonel, that I'm going to ask you. So pay attention.
I'm paying attention now.
The mission robotics vehicle is generating a lot of interest by a lot of companies, a lot of small businesses that want to be on the MRV, right, or the subsequent MRVs. And they have some great ideas. And one in particular, I think saw Kelly Hammond last week in Albuquerque about helping get some background to get in a bit of TAC-5, Strat-5 activity. But the key to that, and it's a transasteric capture back work that they're doing.
I'm tracking.
Yeah,
I'm tracking.
I figured you were. But the question that they came out of that with is yeah, okay, you got the vehicle, the carrier vehicle to get us there, and we got the vehicle to be tested. But those things require some kind of back arrangement of fundings out there to help make this all happen. And in my experience with TAC-5, Strat-5s, which are really great, in the $7 to $12 million range, it's a lot of money to say, hey, these guys will provide some funding for me if you give me the go ahead and go. So the question is really to you is how do you solve that dichotomy of coming up with we have all these great ideas and now we've got the carrier vehicle to do it, but that middle piece is missing. And how do you solve that problem?
If I knew the answer to that, I would have solved it and we wouldn't be having problems. The reality is that I have been trying to figure out how to solve that particular problem for, it took me a year to realize how bad the problem was before I actively started trying to solve it, and I don't know the answer yet. Here is the reality. Most of the funding, this huge chunk of funding, goes to programs of record. That is not a program of record, therefore it gets no money. There is some amount of money that gets carved off into the Small Business Administration pot of money, and it's quite a bit of money, and not in the grand, DOD TOA kind of sense, but it's good money. The problem is the rule set constrains the use of that money, and so when you start talking about something like that, which is a fairly expensive endeavor, it really is. There is not enough money, given the construct of how they decide they're going to spend small business money to pay for the whole thing. Hence the strat-fi TAC-fi. Now circle back around. All of our money is for programs of record. And that is what we, the Space RCO, are supposed to spend it on. That is what SSC is supposed to spend it on, SDA. Sometimes we do that in a way that you can drive a bus through it. You can do some additional things with it. Or you can loosely relate activities to one of your programs of record, or tightly. So for example, our common ground system, R2C2, was tightly coupled with our programs of record, and we taxed our program lines of funding to start working on that until it became a program in its own right. But we manage our money in such a way that we have very little cash laying around at any given point in time. We can still say, I don't know how long this will remain true, that we have never gone and asked Congress for more money for one of our programs, except to buy more quantities of whatever it is we're doing. That's an unusual thing for an acquisition organization. And so sometimes acquisition organizations, their money will, almost always their money ends up out of phase, and then they end up with extra money in a given year. Eventually that bill comes due, but lots of times you can grab money like that to use if you can draw a relationship between what it is you're trying to mature and one of your programs of record. I would say that largely our construct for maturing technology isn't working well for us. And that provides a very real example of an area where honestly it will be very difficult to come up with that kind of money to do the matching funds for the strat-fi. Dr. Lacy does a lot of great work for us, but you're funding limited and you have particular topic areas, and we go tell them, hey, this is really interesting to us, but there is something wrong with our ability to take things from TR level 4 through 6 up through 8 to 9 so that it can actually be used in a program of record. And you do not want to do that in a program of record. That's how they go horribly wrong. One of the ways. There's many. And so I don't know the answer to your question. I wish I did, because then I wouldn't have to keep struggling against the construct that we live in.
But Colonel Stevens, Andy, thanks for the question. I think if you look at autonomy and refueling, and you mentioned being fuel constrained in the future, if it's successful and continues to be successful, and I believe it will be, the air side of the house would not be able to accomplish missions like Midnight Hammer without having fuel logistics trained. And I think you'll see the ability to extend missions to do more missions, and whether it be GEO or others, by having refueling down the road.
Okay, any other questions?
Hi, my name is Jonathan Morton, Right Ascension 231. The OODA loop, the void cycle, is that a useful way of thinking about autonomy? Is there a new, more contemporary way of thinking about that? That's the first part of the question. If it is, what parts of the cycle in your space really take the longest?
Anybody in here a John Warden fan? Yeah,
absolutely.
He pretty much defined modern kind of aircraft warfare, if you will, and like personally designed our construct for going against in Desert Storm, right? If I remember that right?
Absolutely.
It's interesting because in a lot of ways he didn't come up with anything new. He simply created a new mental construct around an already existing idea. But it was a really elegant construct that allowed you to think about what you were doing very meaningfully. Yes, it applies only because it generally applies, period, right? Observe, orient, decide, act. Yeah, and then you circle back around. There you go. Isn't that awful? We do these acronyms and then we forget what they actually stand for. Yeah, 4 is hard. Yeah, 4 is really hard. Give me 3 and I'll do that.
That's right.
All right. So,
Not 10. Not too many. Yeah.
we need to do the same thing in space. And in order to do that, we need a much more mature, robust set of capabilities to be able to observe and meaningfully process that information that I would say currently exists at the moment, and so that you can do the first O. And then and only then can you meaningfully orient and decide and then act, and you circle back around to the beginning. So we need to figure out at any given moment in time what space looks like. Multi-phenomenology, what space looks like. Where are all the objects? What are they doing? What RF emissions are in the environment and why are they there? And on and on. And that will be an enabler to being able to do the rest of the OODA loop. And so SDA is a very important thing. We need to figure out how to do that. We need really smart people and their organizations who can help us process that data and find the meaning in that data. And then at a certain point, when you get sophisticated, and we're like an 18-month-old who's just figuring out how to walk without grabbing a hold of the railing as they go along, right? When we get sophisticated, then we can start finding the meaningful areas of the OODA loop where I should just let a machine do all this for me and then act as a decision aid to help me figure out what I as a human need to do from a human decision-making point of view. So yes, what was the second part?
Of those different parts.
Of those different parts of the loop, which ones really take the longest?
Which one really takes the
Yeah,
longest?
it's kind of like, how would you characterize how that time is changing?
The answer is all of them at the moment, but you want to try that one?
Yeah, I mean, I love this question
Yeah.
because I think it's a really useful construct. I think the observe part definitely takes time, and there's unique kind of autonomy applications just in observing, just in getting space domain awareness information, understanding what is it that I'm actually seeing. The orient part, I think is particularly time consuming because in orient, you're taking what you know from your observations and then you're collecting maybe additional data. In space domain awareness, we found that there is a lot of value in getting both ground and space-based observations, right? If you want to tamp down the error in your ephemeris, it's great to get both. And so, for orient, you need to understand, okay, how do I task additional sensors to get more information? So that's a little more time consuming. The decide part, I think, is really hard. And that's where I think, it's this very unconstrained, very broad set of decision space for what to do And there isn't a lot of great machine learning in the decide space. One thing that we've been thinking about at Livermore for a couple of years now, and we're trying to make some progress on, is this question of if we see, if there's a crisis happening and we see another state taking, a series of actions, what do we infer, right? What do we actually know about what's happening and why it's happening? There isn't really a whole lot out there to help us with that problem set. And this is another area where I think there's a long-term research problem where, folks in the FRCs, there's some other institutions like ours, like Johns Hopkins APL, that are working on this as well.
Game theory.
Game theory could be part of it, but we need some tools to help the operators understand not only what is happening, but why, right? The inference problem. And so that decide piece is also really challenging. I think we're still a long way off there. And then ACT, I talked a little bit earlier about understanding what are some possible courses of action in a constrained RPO space, right? The ACT part is really, really hard because, again, it's a very unconstrained space. And so we need to have some tools and some canonical cases. We need to have an understanding of what the adversary can and can't do. We need to have an understanding of what our systems can and can't do. If we have that, we can put it in a framework and we can use our computational tools, which are better than anybody else's in the world, to get answers to those problems. But ACT is hard too. So really, I think we're still in very early days. I love your construct because it allows you to break down the problem. But I think there's, in particular, that kind of decide and act space. We need more capability.
I'd like to pick up on where your head's at there, but I think that the side piece, there's both we are uncertain about how we want to let our autonomy make decisions. And there are some cases where there's not really a bad option. Okay, none of these are terrible. Some of them are good, but none of them are terrible. Off it goes, let it go. There are others where, like, gosh, I don't know, like, I really want the human involved in that. And in those cases, it's not that the autonomy is going to be allowed to make some very critical decision, but the autonomy can help build those decision aids and say, okay, let me organize the information for you so that you can understand what is happening out there and maybe why. Here are some options for you that the AI may have computed for you. And here are some of the consequences of some of these decisions you might make. And so start thinking, helping the human think through the decide step, I think is a good ripe area for autonomy.
Yeah, I would agree. And the way I think all the panelists broke it down is important. I'll apply a real-world problem to it. If you look at General Gutlein, he's talking about how we see the adversaries dogfighting in space, right? So that decide is really critical. If you see an object coming at you, are they being provocative? Are they being just sloppy, station keeping? Are they being reckless? Why are they so close to you, potentially endangering you in the mission? And so I think when you see and trying to understand intent, it's hard. It's really hard. And I think that, unfortunately, because we do see a lot of these, I would call it very provocative actions by the adversaries, it's very threatening, right? And I said, if you're on the road driving, right, 70 on the road, not 75, right? You're on the road driving, and somebody zooms by you at 90 miles an hour, right? It's very reckless, right? Why are you zooming by? Why are you in such a hurry? And they cut through lanes. It's very dangerous, right? And I think the things that we can do in trying to understand if somebody's being dangerous or threatening, it's really hard.
Okay, we are unfortunately out of time. I think this has been a super, super interesting conversation. So thank you to all of you for all these insights. Thank you, our audience, for your attention and your great questions. And thank you to Redwire for getting us all together this morning.
Before you guys run off, can we do a quick group photo?